This is a talk given at the ASHS annual conference in 2023 in Orlando, Florida. My name is Lillian. I work with Shinsuke Agihara at the University of Florida's Golf Course Research and Education Center, and this presentation is Phenotyping and Characterization of Plant and Soil Nitrogen Dynamics in Winter Strawberry Production in Florida. We've all heard about nitrate leaching and surface runoff from agriculture, but what actually causes it? According to the scientists who have looked into the question, it's excessive nitrogen input, where the supply of nitrogen exceeds the demand of nitrogen from the plant. Therefore, the challenge for anybody who is concerned with this issue in agriculture is to match the nitrogen supply with the nitrogen demand, because if the plant takes up the nitrogen, it does not get into the environment and the plant grows. In collaboration with that idea, my objectives are to characterize growth stage specific nitrogen requirements so I can determine the demand of the strawberry plant in general throughout the season, and to identify traits associated with nitrogen uptake and use efficiency with the hope of using these traits to determine when nitrogen is needful in the season. For the 2022-2023 trial that we did, we used 4 common Florida cultivars. We used Brilliance, Sensation, Medallion, and Pearl. These particular cultivars might not be eternally important, say in like 20 years. However, it is very important to use multiple cultivars when trying to do a trial like this so that the model that you create is robust and can be applied to multiple cultivars. So these are also commonly used cultivars, and so in the short term, it should also be useful for growers who are using these cultivars specifically as well. The soil in Florida, in particular in Plant City, is very sandy, so it's like hydroponic growth medium. We used a randomized complete block design for my study. We used 4 applications. The data that we collected was canopy projected area, yield, tissue and soil analysis, including nutrient analysis, unmanned aerial vehicle imaging, BRICS, which is the sugar content, and hyperspectral imaging. Explaining a little bit about conventional fertilization for strawberries. We actually do something called fertigation, where the irrigation water and the soluble nitrogen fertilizer go out by the drip tape at the same time. This usually occurs after the overhead irrigation to keep the plants cool after they're planted is turned off, and then it begins with 2.2 kilograms per hectare per day of nitrogen during establishment for the first 21 days, and then 1.1 kilograms per hectare per day of nitrogen for the rest of the season. So worth pointing out, we actually begin with a high fertilizer rate and go to a lower fertilizer rate. So strawberries are backwards in that sense. The reason that the growers do this is the strawberry plants are grown originally in California and Canada and then shipped all the way across the country to Florida. And so they're uprooted, their roots are exposed. This makes the roots unable to uptake large amounts of water when they're initially planted. And that means that they can only uptake just a tiny little bit of water, and so you want that tiny little bit of water that they can uptake to be jam-packed full of nutrients during the establishment period. The unfortunate side of this is that they only take up a tiny amount of the fertilizer that is applied during this time, and the rest is lost, which is kind of the focus of my dissertation, and applies somewhat to the current study at hand as well, because we're trying to figure out the demand of the plant to better sync these fertilizer habits, get it delivered to the plant appropriately. Statistical analysis, we used ANOVA for differences between cultivars. We're not going to go over those results as much in this presentation because we're more concerned about the overall modeling of the nitrogen needs of the plant. More important for this presentation is the regression analysis over time. For that, we used sigma plot, and for the different parameters, we used a p-value of 0.05 to determine whether they would be included within the equation. And then for the different models that we modeled off of, including linear, quadratic, exponential plateau, exponential decay, and sigmoidal, to determine which was the best fit model, we used the AICC criterion. We also did correlation analysis for correlating different data sets. This is especially important with the unmanned aerial vehicle imaging, correlating to the other data sets. For this, we used the R program. We used the plot and core plot functions and R2 as our determining factor to see how strong the correlation was. I mentioned that we got canopy projected area as one of the data sets. And way of explanation for what this actually is, it begins as a red, green, blue typical RGB image, and then we put it in image J and create a binary image. Basically, we capture a narrow spectrum of color that includes the leaves, and with this, we can estimate the overhead visible leaf area, which is what the canopy projected area is definitionally. We do something similar with the image processing of the unmanned aerial vehicle photos, including the RGB, NDRE, NDVI, and NIRE. Except in this case, you can see something called NIR, which is near infrared, and then red edge. These are outside of the visible spectrum of light. In way of explanation for what these different indices are, RGB, of course, stands for red, green, blue. NDRE, normalized difference, red edge. NDVI, normalized difference, vegetation index. NIRE, near infrared, red edge ratio. What these ratios are telling us, basically the near infrared and the red edge light outside of the visible spectrum, they are output by the plant, I guess you could say, reflected by the plant based on the chlorophyll activity within the plant. And so this can actually tell us what's happening inside of the plant right now, and then potentially be used as a predictive indice for what will happen to the plant in the future based on the physiological activities within the plant. So we sampled some plants for the nutrient analysis. We did 9 plant samplings throughout the season, which consisted essentially of 2 plants for 1 composite sample. We also took soil samples throughout the season, consisting of 6 cores for 1 composite sample. We did it about bi-weekly for the plant sampling and about monthly for the soil sampling for a rather long plot. We had a couple of edge plants and then plants to sample and the cores to take and everything. What was actually very exciting was that we got a sigmoidal nitrogen uptake pattern, a very strong one with an R2 of almost 1, which is definitely not an accident of any kind. And we actually got this more than for total nitrogen uptake. We got it for the nitrogen uptake of the roots, of the shoots, including the leaves and stems, even the fruits for all cultivars except for 2. So 2 of those cultivars were showing a quadratic pattern, which based on the other cultivars, we showed the sigmoidal. Ultimately, if we continued to take yield data over time, that would most likely have resolved into a sigmoidal pattern as well. So regarding the unmanned aerial vehicle indices, they didn't actually correlate with nitrogen uptake at the same date. How do I know? Let me prove it to you. You can see that there's a dip in the indices and a rise in the reflectance at the end of the season. And now take a look at the nitrogen uptake. In that same window at the end of the season where you have the dips and the rises, there's no big rise or fall in the nitrogen uptake. And so that kind of tells us that the UAV indices don't correlate with nitrogen uptake at the same date. However, the UAV indices may correlate with physiological changes within the plant, which I mentioned before about other people have found that it correlated with chlorophyll activity. So in way of explanation for why there might have been these dips and rises at the end of the season, just take a look at what happens after we didn't harvest a plant a week out like we normally do, because we were harvesting weekly and everything. After we didn't harvest, then we have the dips and the rises. And one explanation for this is in nature, plants will continue to produce fruit as long as you continue to pick fruit. When you stop picking fruit, then the plant thinks that it has reached the end of its life cycle, it's happy, and so now it can relax. If you keep on stealing babies, it keeps on having chlorophyll activity. If you stop stealing babies, then the chlorophyll activity will ultimately kind of start to peter off and everything, and then you'll start to see other things happening within the plant. That's one explanation, possible explanation. Another explanation is we did have low soil nitrogen at the end of the experiment, similar to before we actually applied nitrogen. We're suspicious that perhaps the farm crew might have stopped applying nitrogen a little bit earlier than they said, which would also potentially cause a decrease in the chlorophyll activity inside the plant. We did find that the unmanned aerial vehicle indices correlated with nitrogen uptake and weekly yield 4 to 5 weeks out. So this might be possibly a delayed reaction from physiological changes inside of plants. So then the UAV indices today, increased chlorophyll activity today could result in increased nitrogen uptake 4 to 5 weeks out. That's basically what we're looking at. So the strongest correlation of this kind was with the near-infrared red edge paired with total nitrogen uptake and marketable yield. Anything that's an R2 of more than 0.5 begins to be almost certainly not an accident. So these were the strongest. This is when they peaked about 4 to 5 weeks out, looking weekly and everything. The total biomass, unmanned aerial vehicle, ground cover, and canopy projected area positively correlated with nitrogen uptake at all dates. The max delayed peaks was once again 3 to 5 weeks out. So once again, the images that we took, and then also the destructive biomass measurements we took, correlated well with the nitrogen uptake 3 to 5 weeks out, in particular, beyond the original date. So then, same deal here. Total biomass, unmanned aerial vehicle, ground cover, and canopy projected area also positively correlated with yield at all dates. Once again, peaking at 3 to 5 weeks after measures. In summary, the strawberry nitrogen uptake in the 2022 to 2023 growing season matched a sigmoidal pattern with a high statistical significance, providing overall guidance for strawberry nitrogen application timing. It also may be possible to quantify the future and nitrogen needs of strawberry plants within the same season using biomass data, overhead images, or unmanned aerial vehicle images. So if you know when the yield is going to be coming 3 to 5 weeks out, then you can plan when to bring in your labor. If you know when the nitrogen uptake is going to be the greatest 3 to 5 weeks out, then you can plan how much nitrogen to apply. So this could potentially be pretty important findings, and not too difficult to actually take the unmanned aerial vehicles or even the other types of data. And then hyperspectral analysis is coming soon. In regards to discussion, modeling the future nitrogen needs within the same season using regression analysis may require increased statistical power. So I mentioned that we got just an incredible R2 for doing the regression analysis, just with that lovely sigmoidal pattern and everything. So that gives us some general guidelines. But if we wanted to get guidelines in the same season, we would have to do regression analysis between the unmanned aerial vehicle imaging and then the other data sets. And in order to get enough power to be able to do that, ultimately we most likely need to get plant level data, take down from more plots or more sampling dates, at least with a few of the different data sets. Potentially you might be able to get away with it with some of the biomass readings. And then one possible explanation for why higher biomass results in greater yield or biomass 3 to 5 weeks out may be the association of biomass with flower bud initiation. So if we have higher biomass today, ultimately that would potentially result in more flowers being formed today. Assuming that nothing catastrophic happens to the plant between now and 3 to 5 weeks from now, more flowers today would mean more fruit 3 to 5 weeks from now, because it takes 3 to 5 weeks for a fruit to form from a flower. And then also picking fruit at this date may also stimulate new flower production, as I mentioned before, resulting in higher yield 3 to 5 weeks later. Acknowledgements. This is my team. They're great. I'm always learning from Dr. Agihara. He's a wonderful professor, and I'm very, very thankful for all my team, and I couldn't have done what I did for this experiment or any of the experiments that I work on without all their help. And then I also have to thank my baby and my husband, who I wasn't spending time with because I was spending time on this. And then, of course, I put up a couple little prayers and everything. That's when I started having most productive thoughts. So from a scientific perspective, that's worth noting as well. If science was light, my team is the sun, moon, and stars.